So about 10 years ago now, there was a guy named Frank Graziani, who I think many of us know. Is he here? Is Frank here? No, he's not here. Okay. Okay, all right. Who started a collaboration called Cimarron, and it involved these people that you see here plus a few others, okay? And it was a very lively group of people, and one of the most important was our guest of honor here. And so I'll be speaking variously about his contributions to this particular topic throughout. So I'm going to talk about temperature equilibration. So what is that? Well, in plasma physics, this is the problem of having an interleaving gas of electrons at one temperature and ions at another temperature. Okay, so for instance, if it was hydrogen, just electrons and protons. And the simple question, seemingly simple, is how long does it take for them to reach a common temperature? Okay. And the first person that I know of to think about this, although I believe he was actually considering it in the context of gravitating objects, was Lev Landau in the mid-1930s. And it's important for understanding fusion burn rates in a plasma, since the burn rate is such a sensitive function of the ion temperature in things like inertial confinement fusion, for instance. And there are various places where the electrons are predicted to be hotter than the ions, or the ions predicted to be hotter than the electrons, depending. And so to get the burn rate right, you want to know the temperatures of the electrons and the ions very precisely, and this is one term that forces them to want to be similar. So that's the problem that we were interested in. I should mention that Cimarron was actually interested in many problems, alpha particle stopping and a number of other things of interest to ICF, and so this is just one of them. The other thing I should say is that, of course, one of the other things that's very important here is radiation. I'm not going to be talking about radiation at all. This is going to be the first talk that doesn't mention anything about radiation. We should and hopefully will at some point consider that as well. But even just the problem of mutually scattering Coulomb particles is already complicated enough, as I'll show. Okay, so let me go into a little bit of a description of the classic thing that Landau did, augmented later on by Lyman Spitzer, initially at least by Landau in the 30s. So there's this thing called the Landau-Spitzer equilibration time. So this is this time for the electrons and ions to get to be the common temperature when they start at two different temperatures. And the argument goes like this. Well, we want to use kinetic theory. We want to use something like a Boltzmann equation to do this. But we have this pesky collision term. And if I consider all possible, let's say, interactions between a given electron and a given ion pictured there, okay, well, I have to sum over all possible center of mass energies, and I have to sum over all possible impact parameters, okay, and that's the impact parameters B there. When I do that, and then when I try to compute this energy transfer by doing that, just one collision at a time, okay, then I get a bit of a conundrum, because the integral that I have to do is something that looks like integral of dB impact parameter divided by B. And that logarithmically diverges both for small b and large b, and that gives rise to the famous and infamous Coulomb logarithm, which people in this business have talked about for many years. And so what Landau specifically did was he used not quite the Boltzmann equation, but he used the Fokker-Planck equation, which is basically like a Boltzmann-like thing, but for small angle scattering, which for various reasons is the thing to do for these Coulomb scattering problems. And he was very brilliant, and he made a couple of interesting physical onsets. The first one is that, well, the small b logarithmic divergence is actually kind of inconsequential, because let's say, just an ideal situation, that I only had one electron and one ion in the whole universe. I mean, they're going to have some initial kinetic energy, and that's going to actually determine what their minimum impact parameter is. There's going to be a sort of classical turning point, assuming that the idealization of a point like electron for the moment. Okay, and then so that kind of eliminates the minimum impact parameter part, but the hard part is the maximum impact parameter part, which really can only be dealt with when considering the fact that, of course, in an actual plasma, you don't just have two particles scattering. It's not a binary scattering process. You've got a whole mess of particles, and any given scattering process is going to be mediated by screening from all of the other spectator particles. So in particular, if my impact parameter was significantly larger than a Debye screening length, well, that's a pretty natural place to cut off that logarithmic integral, and that's exactly what Landau did. So if you had classical electrons, that would be an answer, okay? Of course, in a lot of the things we care about, let's say at the National Ignition Facility, we're in conditions where quantum part of the scattering is very important. meaning really that this electron has a thermal de Broglie wavelength associated with it, which if it is larger than the classical turning point distance, then the natural thing to put in the minimum there of the B min is actually the thermal de Broglie wavelength. So that's the sort of setting the stage for what this problem is about. So because we have big computers here and we've had them for quite a long time, we thought, well, geez, I mean, is this Landau-Spitzer thing correct? I mean, you're making all these so-called weak coupling approximations, small angle scattering approximations, binary scattering approximations with this effective screening medium. Is this all baloney? So the first thing that not just us, but people at Los Alamos did, going back a little ways, was to use classical molecular dynamics to try to actually set up a non-equilibrium problem where you have electrons at one temperature, ions another, and then see how long it takes for them to equilibrate. So a number of us tried to do this over a span of a number of years. The first thing that was done is actually, I have to say, my favorite. The second name here, Guy DeMonte, is probably familiar to many of you because he used to work here. But then after he moved to Los Alamos, one of the many things that he did was to do this problem, but now for classical electrons with like charge. So this is positrons and protons rather than electrons and protons. That way you avoid the nasty problem of electrons being, these classical electrons being captured by their protons and getting into, a Coulomb catastrophe, which quantum mechanics, of course, mitigates. But if you're going to do a classical molecular dynamics simulation, you want to avoid that. And so they did that problem. It turns out that then you can also apply a Landau-Spitzer-like theory, and it should also give you the same sort of answer, even though you now have repulsive particles rather than attractive particles. And they measured, basically computationally, a bunch of different rates for different initial starting conditions, compared it to a number of different theories. So that was maybe the first example of this. And then what we did, starting actually in the beginning of Cimarron, but before John Castor joined us, but involves a number of people in this room, was to do this for hydrogen plasmas, but where we used something called a quantum statistical potential. So what is that? What this is it's a kludge to the interparticle interaction, which mocks up the effect of the electron having a thermal de Broglie wavelength of some finite extent. Okay, so basically, this is the electron-ion pair potential as a function of the separation between a given electron and a given proton. Blue would be the Coulomb potential, and then this is what this effective quantum statistical potential would be for different choices of electron temperature. Okay, this would be a very low electron temperature. This is a higher electron temperature, and basically, the Coulomb interaction is softened within a thermal de Broglie wavelength. So if I have an electron coming like this, even though it's a classical point-like particle, it's interacting via an effective interaction that mocks up the fact that in quantum scattering, I'm going to scatter through, on average, a smaller angle than if the thing was actually undergoing a Keplerian orbit. Okay, and so this has been used for a number of years. We didn't think of it. It's actually been around, the idea, since at least the 1960s. But now we can do a bunch of simulations where we put electrons at one temperature, ions at another temperature, and then monitor their kinetic energies as a function of time using this kind of simulation. And so what we did is essentially map out for plasmas of interest an effective Coulomb logarithm. This is basically just proportional to the rate that I'm interested in, and then we can compare that to different analytic expressions for Coulomb logarithms that people like, for instance, George Zimmerman sitting over there had put in rad hydrocodes to do ICF-related problems. And we could say, okay, well, for a strongly coupled plasma, let's say one, for instance, with where either the Z of the ion is large or the ion temperature is low, maybe the formulas have to be modified in certain ways, and that's the kind of game we were playing. So that's what we did in the beginning. That occupied a couple of years, but it was still basically comparing the MD results to analytic expressions rather than really trying to understand theoretically what's going on. And then we were talking with Michael Murillo, who was at Los Alamos at the time, kind of helped to push us in the direction of this overarching strategy. Well, let's do those same kinds of things, but now compared to, and I'm sorry I didn't spell this out, classical Lenard-Bolescu theory using the same interparticle potentials. So Lenard-Bolescu is it is a kinetic equation, but now where the collision term involves a dielectric function. So now the screening is in the dielectric function, But this screening thing has to know about the distribution function in the kinetic equation, so it's a pretty complicated beast. But for a problem like temperature equilibration, you can solve it perturbatively and get, again, analytic expressions, but they're a lot more complicated than the Landau-Spitzer thing. So let's do that and make these comparisons. And so we started doing that, and right around the time we started doing that, this guy showed up. Okay, so he started coming to our meetings. He wasn't initially a part of this, but he started to be interested. I think probably he was mostly interested in things that Cimarron was working on that actually did pertain to radiation, but again, that didn't play into this specific problem the way we were doing it. So we did the same stuff again. We redid all of that, but now comparing to really the state-of-the-art sort of many-body theories for a problem like this to see if we could make apples-to-apples comparisons between the MD and the kinetic theory, including the screening from first principles in some sense, to see if we could derive the appropriate Coulomb logarithms and really see if we understood what was going on. So it's a little involved, and I'm going to skip a lot of the details, but just to say that, again, I have to go back to this wonderful paper of Jerome Dalago and Guy de Monti, where they sort of laid out a roadmap for how to, in a sense, derive the Landau-Spitzer thing from first principles, in a sense. And so we took this a little further by saying, okay, well, you can apply this to the actual quantum hydrogen plasma, or you can say, I want to understand the MD that we're doing. We're doing this classical MD with these weird buggered potentials, which have this effect of the thermal de Broglie wavelength kludged in, as I mentioned. Let's actually apply this prescription to those systems in a literal sense to see if we can understand, can we model the MD? My thinking was that, if we can't do that, then we have no business actually tackling the quantum plasma. So let's see if we can do that first. And there is an interesting quantity in here, which basically this is called a local field correction. So essentially, the way that this whole theory works is that the coupled density fluctuations of the electrons and of the ions is what drives the equilibration. And so that means you need to be able to calculate the density fluctuations of these electrons and ions individually. And what I mean by fluctuation is, let's say you've got a gas of electrons. I come in with some external potential and I kick the electrons in some way. How does the density respond to those? And of course, when the density does respond, that's going to produce another potential, which is going to be seen by the electrons again and the ions. And there's a self-consistent field problem, and that's what's called that's what's usually solved by something called the random phase approximation. If you tack on this factor, which is this so-called local field correction, what that does, or what it purports to do, is to correct for basically effects of stronger coupling. Basically, when you have the electrons and ions, or the ions and the ions getting very close to each other, that mean field approximation doesn't work anymore. And so it's basically a way of going beyond that, which is necessary to handle a lot of the situations we're interested in. Well, so the first thing you can do is you could do this pain in the butt double integral. So this is, it's not that complicated in the sense that we're dealing with a homogeneous plasma, so we just have to integrate over wave vector and integrate over frequency, and that's it. But these are complicated functions that have poles because of this dielectric function in here and all of that. That's the two species dielectric function, so plasmons live in there, for instance. Okay, but so if you integrate if you do the omega integral and then you're left with just a k-dependent integrand, boy, it looks a lot like 1 over k. Well, guess what? That's the Coulomb logarithm. Okay, so you get, this is essentially what I meant when I said that this can be thought of as the derivation of the sort of Landau-Spitzer prescription. Okay, so that's at small k, which corresponds to large distance. That's where the dielectric function is cutting the thing off. Okay, so that's giving you the maximum impact parameter. And then quantum diffraction comes in and gives you at large k, or small distance, that gives you the minimum impact parameter. And the more weakly coupled the plasma is, the more there's the wider range of k over which this looks like 1 over k. So you get the Landau-Spitzer result, but you're now deriving it. You don't assume this. It's actually something that's coming out. So, one of the things I learned very quickly was that, and this was actually echoed in Richard Klein's talk, I wrote a code to do these complicated integrals, and Castor was doing a similar thing, and we were always getting slightly different results. And I'll be damned, every time that we got a different result, he was right. So I echo your point and your frustration. Anyway, So one of the things actually that allowed him to get a much better result, even with a code that was much more efficient, was that he figured out that for this problem, if the thing looks like 1 over k, maybe you use a quadrature scheme that benefits from that. So that's one of the things that we ultimately did. And I slowly made my code look more and more like his, which is what I had to do to get the right answer. And another thing that he did, which was really good, is I talked about this local field correction factor. We didn't have a means to calculate that. And in fact, he is not an expert in this field at all, although now he is. He looked into the literature and learned about the hyperknitted chain approximation and wrote a code on that. So this is basically something deep within the annals of liquids, of the theory of liquids. And it was exactly what we needed to basically to do the computation to sort of close this whole prescription and get predictions. And so basically what this is just, it's sort of a potential of mean force concept. So if I have a particle here and a particle there, there's some effective force between them that is informed by the fact that there's all these other particles that are mediating their interaction. And so that was a very complicated problem that he helped us to solve. And it was important because then we could address the question, well, if we get disagreements between the MD and the theory, are they because we've screwed up the static structure of the plasma, or is it because of something intrinsic to the dynamics of the scattering? Okay? So what John helped us to really realize is that, yeah, actually, we had the static structure of the plasma correct. So this is his HNC calculations of the static structure. So this is a radial distribution function. So the conditional probability, if you're sitting on one particle, what's the probability of finding another one of the particles some distance r away from you? And so we measured that in the MD, and we looked at John's calculations, and they were right on top of each other. So that was great. And that meant that any disagreements that we see in the rates are due to more interesting effects. And we did see interesting disagreements. And so this is basically the d temperature of the protons d time when I have the protons initially being hotter than the electrons. And this is for a class of different plasmas where I'm ramping up both the electron and ion temperatures, but they're 20% different from each other. And I look at the rates at which they approach each other as time evolves. The pink dots are the MD results of Mike Sir, okay, using these Jimmied interactions. And then the green are what we would get from this generalized Lenard-Balescu prescription. But the interesting thing is that we get a worse result if we don't include this, or if we get a worse result if we do include this so-called local field correction. So that's something we still don't really understand, but it's very interesting. So how much time do I have? 7 minutes. Okay, so I'm going to skip that, although that was an interesting contribution of his too. Okay, the whole point of doing all this stuff is really to head into regimes where we don't know what the answer is. In other words, where we're sure that the Landau-Spitzer rate or anything like it is definitely going to be wrong, or at least we have no reason to think that it would be right. That's where we want to use this MD approach. Okay, so it was predicted a number of years ago that if you have strongly coupled ions, that means if the ions are either have a large charge or if their ion temperature is very low, even if the electrons are very weakly coupled, that could head you into a regime where you get a different answer than what we've typically assumed. So we wanted to look at that. We call this the coupled mode regime. So, and it was initially, I think, a nice paper was written in the late 2000s by these guys, who are friends of ours. And so here's the cartoon of what this is. So if the ions are fairly cold, okay, and the electrons are fairly hot, well, actually, forget about that. In any kind of electron-ion plasma, I mean, you have the following phenomenon. You have something called an ion acoustic wave, which is basically, so let's say that we had only electrons in a positive uniform compensating background. If you kick that system, the electron density is going to oscillate like this. That's called a plasmon. And the long wavelength version of that mode has a very sizable non-zero frequency that depends on the density of the thing. That's called the plasma frequency. If you have electrons and ions together, well, what happens is the electrons, some subset of them, will form screening clouds around the ions. And then if you look at the effective ion-ion interaction, well, that's going to be a lot weaker because it's already been deadened by the fact that you've got electrons around it. And so that looks more like two neutral objects, which means that if you've got two of those guys far away, that's not an electrostatic force, that's an exponentially decaying force because of the screening. And so what that means is that the plasmon in the two-component plasma at small, a small wave vector or a long wavelength ends up becoming a sound mode, basically, or where the frequency goes as the wave vector, not goes as a constant. That's really important because actually the theory that I mentioned before, you can think of temperature relaxation or energy exchange between two different species of particles as being mediated by the exchange of plasmons, absorption of, emission of plasmon by one oscillating thing and absorption by another species. So if this thing is happening and if it's a significant effect, that can dud the equilibration rate because these things are going to be much less efficient for transferring energy simply because, well, I've got the electrons moving doggedly with the ions. If I move an ion, electron moves with it. That's not resistive heating of one species off the other. So, that's, we have to be mindful of that. So we did some calculations where we predicted what the effect of this would be, and it sure enough is a very big reduction, which is for the conditions that if you set the conditions up right, which in our case we did hydrogen, but we made the electrons be 10,000 or something times hotter than the ions, which, by the way, incidentally, you might get if you did laser excitation of solid density matter. You might be in a situation where you have much hotter electrons and colder ions. And so that is indeed, at least within the theory that I've shown you, predicted to give you a substantive reduction in the rate. So now let's do the MD and see what we get. Well, I don't have enough time to show all the vagaries of this plot, but let's just, you can just take my word for it. You actually don't get a big reduction. And so that was a bit of a mystery to us. And so first of all, when we saw that, I was talking to John about it. And I was asking him, because I never really fully understood the reduction in the first place. I mean, I gave you a hand-wavy argument in terms of these balls of things moving around, but the math was a little dicey, for me, at least in my head. Well, in true John Castor form, he went away and actually wrote a little mini paper where he dissected exactly what's going on, at least within the rubric of the theory that I presented, as to why you might get a reduction like this. Because at first, we weren't sure even that these other guys were correct. I show this because this is one of a few examples of where I've worked with John where he's done this, where he's gone off and written a little mini paper. There is another pertaining to the hydrogen equation of state, but that's a different subject, so I'm showing you this. But this is almost publication ready. I mean, it's extremely clear, and it's like a textbook. So we now understand that what probably was going on is that, well, when you have the ions being very cold, okay, so they're fairly strongly coupled, their density response is not the density response of free particles, like as would be predicted by the so-called random phase approximation that I mentioned. That means that their collective excitations live much shorter time than what would be assumed in the theory that I showed. And if you take that into account, which John helped us to do, by the way, by evaluating some the Dawson function for complex arguments, we were able to actually show that exact effect is probably what's giving rise to the fact that this coupled mode effect is not something we actually see in the molecular dynamics. So the big point is that, why did we do all this? We did all this because we want to make sure that the coefficients that we have in rad hydrocodes that we use are producing the right stuff. We want to do direct numerical simulations to test those things where we can, especially, I didn't mention this, for this quantity it's notoriously difficult to measure it experimentally, although there are important experiments underway to do just that. So that was very good, and actually we were initially worried that, well, geez, I mean, if we have more strongly coupled ions, like you might have, for instance, if you have, let's say, some of the ablator material making its way into the fuel in an ICF capsule, for instance, then maybe, the accuracy of some of the things that we'd be doing would be undermined. This is actually a good news because it looks like this thing that would have undermined it maybe is a much smaller effect in reality. And I could just say that John played a major role in every aspect of this to try to, help us understand these things. So the most important concluding statement, of course, is this.
Questions? Stan? Wait.
Is the scientific bottom line that the classical formulas are better than you expect and they go all the way, I mean, it sounds like these more complicated corrections are all kind of going away, and that
So far, yes.
classical,
So far, yes.
the bi-shielding formula is pretty good.
So far, yes. But again, I don't want to stick my neck out too far. But we were surprised by this, but
Okay.
so far, yes.
Okay. I mean, just as a comment, the similar thing happens in Sobolev theory. It turns out to be much better than you expect to be.
So I'd love to hear maybe that story just offline. I'd
Okay.
like to learn about it.
We have time for one more. Okay, let's thank the speakers. Oh,